A prime number is a positive integer that has exactly two positive divisors, one in itself. For example, 2, 3, 5, 7, and 11 are prime numbers. A twin prime is a pair of prime numbers that differ by 2. For example, 3 and 5, 5 and 7, 11 and 13, and 17 and 19 are twin primes. There are infinitely many prime numbers, but it isn't known if there are infinitely many twin primes. This is called the twin prime conjecture, and it is one of the oldest and most famous unsolved problems in mathematics. Now that we have defined what twin primes are, let's see how we can measure their density. One way to do this is to count how many twin primes are there up to a certain limit. For example, there are 8 twin primes up to 100. We can denote this number by pi2 of 100, where pi2 of x is the function that counts the number of twin primes with the smaller at most x. In general, we can write where the capital P is the set of prime numbers and hashtag denotes the cardinality or size of a set. Pi2 of 10 equals 2, because there are only 2 twin primes with smaller at most 10, 3, 5 and 5, 7. The function pi2 of x gives us an idea of how frequent or rare twin primes are as x increases. Another way to measure the density of twin primes is to look at their reciprocals. That is, instead of counting how many twin primes there are up to a certain limit, we can add up their inverses. For example, the sum of the reciprocals of the twin primes up to 100 is equal to around 1.33. We can denote this sum by S2 of 100, where S2 of x is the function that sums the reciprocals of the twin primes with the smaller at most x. In general, we can write S2 of x as the sum of all prime twins, where the capital P is the set of prime numbers. The function S2 of x gives us another idea of how frequent or rare twin primes are as x increases. But what happens if we let x go to infinity? Does S2 of x converge to a finite value, or does it diverge to infinity? And if it converges, what is its limit? The answer to the question of whether S2 of x converges or diverges was given by Viggo Brun in 1919. He proved that S2 of x converges to a finite value as x goes to infinity. This means that the sum of the reciprocals of all twin primes is a well-defined number, even though there may be infinitely many twin primes. This number is called Brun's constant, and it is usually denoted by b2. In other words, we can write b2 as limit as x approaches infinity of S2 of x. The exact value of b2 is not known, and it may be irrational or even transcendental. However, we can estimate b2 by computing S2 of x for large values of x using computers and algorithms. The computation of b2 is not an easy task, and it requires a lot of time and resources. The first person to estimate the Brun's constant was Brun himself, who used all the twin primes up to 2 million and obtained b2 equal to around 1.9. Later, other mathematicians improved this estimate using more twin primes and better methods. For example, in 1976, Richard Brent used all the twin primes up to 10 to 11th power and obtained a closer approximation. In 2002, Thomas Nicely used all the twin primes up to 10 to the power of 16 and obtained even closer approximation. Besides twin primes, there are other types of prime constellations that can be used to define similar constants. One of them is prime quadruplets, which are sets of 4 prime numbers of the form p, p plus 2, p plus 6, and p plus 8. In other words, a prime quadruplet is a pair of 2 twin primes separated by a distance of 4. For example, 11, 13, 17, 19, and 101, 103, 107, 109 are prime quadruplets. All prime quadruplets except 5, 7, 11, and 13 are of the form 30n plus 11, 30n plus 13, 30n plus 17, 30n plus 19 for some integer n. It is not known if there are infinitely many prime quadruplets. The constant representing the sum of the reciprocals of all prime quadruplets is called Brun's constant for prime quadruplets, and it is denoted by b4. In other words, b4 is equal to this sum, where the capital P denotes the set of prime numbers. The value of b4 is approximately 0.87.